Hi, today we're going to talk about the moment of inertia. And to do this, we're going to use the Pasco moment of inertia system, which will allow us to measure the moment of inertia of various cylinder type devices. What we're going to do today is we're going to start off by taking measurements of 3 different cylinders. We are then going to calculate out, using the moment of inertia formulas that we have been given, the actual values for the moment of inertia based on the mass and the radius of those cylinders. After we've done that, we'll experimentally find if those values are correct. So let's get started. First, we have here the Pasco moment of inertia system. And as you can see here, there are a number of parts that are included in this experiment. We are going to take this cylinder and we are going to have it pulled on by this string. There's a step pulley underneath, and we'll use this step pulley's radius later on. We're using the largest step pulley, but ultimately, if we wanted to, we could do this experiment with 3 different torques, because there would be 3 different radiuses pulling at a distance on this. So we need to measure both the radius of this cylinder, and we need to measure its mass. We're also going to be using this pulley system here that's called a smart pulley. This system has on it a photo gate that is going to calculate the angular displacement of the wheel. As the wheel goes along, the spokes block the photo gate laser, and that is going to cause the sensor to send a signal to the computer that will be recorded with time, and so we'll be able to find out the displacement, as well as, since we have the time, we'll be able to find out the angular speed. What we're going to be looking for is angular acceleration, and then converting that into linear acceleration. So using theta r equals x, and omega r is equal to v, and alpha r is equal to a acceleration, we'll be able to calculate this out. So we'll use angular measurements on here, and then knowing the radius, we'll be able to calculate out the linear acceleration. We'll use a graph of velocity and take the slope of it.
So now let's look at the math related to the Pasco moment of inertia system. You can see here that we have a picture of the system. We have our table with the Pasco system sitting on top of it, a pulley over on the right, and a hanging mass hanging off the pulley. And so just like we have done with other systems, whenever we want to talk about force, we use Newton's second law. We say acceleration is equal to the sum of the forces divided by the mass. And so in this case, there's the hanging mass pulling in one direction, and there is the Pasco system creating a tension in the backwards direction on this system. And so we would say something like acceleration is equal to mg, that's our hanging mass's weight, minus the backwards tension caused by the system, divided by the mass of the combined system. That can be rewritten, solving for tension, to say something like the tension force is equal to mg minus ma, where a is going to be experimentally found, and that will be what we're going to measure with the smart pulley system in a few moments. This T is causing the torque, and depend on the pulley system, and depending on which step of the pulley system we're using, that's going to determine the acceleration of the overall system. Since torque is equal to force times the distance, we know that by changing the radius, we're going to change the overall torque on the system. Again, this force is going to be the tension caused or measured in the system. The steps pulley size does affect the overall acceleration. An alternative concept that is going to get connected in here is the idea that torque is equal to the moment of inertia times alpha. And keep that in mind that we have a linear and an angular form of this. And so the angular acceleration is equal to A over R. And we get that from the concept that we learned previously, that x is equal to theta r, v is equal to omega r, a is equal to alpha r. And so by dividing both sides by r, we get alpha. Now what the Pasco system is going to do is it's going to solve for that angular acceleration. It's going to take the step pulley, it's going to measure the displacement in angular measure of that step pulley. It's going to know the radius, and so it's going to say, okay, theta's displacement is a certain amount times r, which is set in the system. That's going to give us x. It's going to use the time component that it gets from the photo gate, and it's going to say, okay, that displacement x divided by t is v. We're going to graph that velocity, and we're going to do that in multiple measures per second. And then we'll be able to take the slope of the velocity versus time and get our acceleration. But ultimately, we're using this concept down here to convert between angular and linear forms. Now, with that said, we can do a substitution here, and we realize that the torque is equal to, again, I alpha. And so if we substitute in our A value, we get T is equal to, or torque is equal to I times A over R. Or in other words, when we solve this out, we will get the torque times the radius divided by the acceleration is equal to I. And using this concept, we can solve for the moment of inertia experimentally. The connection piece here is right here, that if we can solve for the acceleration, we can substitute that in for the torque, then we can work our way through the experiment to solve for I. And that I value will be our experimental moment of inertia, which we will compare against our theoretical moments of inertia for this experiment. At the end of this demonstration, that lab activity, we'll go through the math a little bit more, but this is the foundation that we need to be thinking about as we move through this experiment.
So going into the Pasco system, we are going to set up on the gate 1 channel, the photo gate with pulley. And this is pre-set up, whereby we've bought the system that works together, but you could adjust for the arc length and the spoke angles. In fact, some of the spokes angles for some of the pulleys we have are actually different. This system has 10 spokes. Some have fewer, some have more, depending on the precision we want to use. Again, our arc length based on the laser's location is 0.15 meters. We are going to use a graph of speed, linear speed, and find out the acceleration by taking the slope. Again, what the system is doing is it's going to measure over here, it knows the radius, it knows the angular displacement, it's going to use theta r to get us a distance, it's going to use the time between when the photo gate is blocked to give us a velocity. And so they work together using our angular concepts and converting them into linear. Okay, so what we want to do is we want to take, and we get over to this table, the masses of our 3 devices, our 3 discs. And so I'm going to take the main disc, that's the one with the step pulley. I'm going to place that on the balance. And I get 724 grams. While I'm working with this, I'm going to measure its radius. I'm going to find that by measuring across and making sure that I find the point where it's greatest, so that way I know I'm measuring across the largest chord, which we refer to as a diameter, and I get about 25.4 as the diameter. So I need to convert that diameter into the radius. I let the computer do the heavy lifting for me. So I'll do equals 0.254 divided by 2. I then am going to do the auxiliary disc. The auxiliary disc has a mass of 640 grams. We'll measure its diameter. To do that, again, we're making sure that we're measuring across the circle and making sure that we get the point where it's the greatest. That would be the diameter. This one comes out to be about 25.4 as well. 25.4 as well. Make sure we convert into meters. And then we have the ring. And the ring has a mass of 704 grams. And it has a diameter, when we measure across, make sure I'm measuring in centimeters, not inches, about 12.7 centimeters, so 0.127, and we want to divide that by 2. And then we are going to calculate using the equations that we've been given. So for the main disk, that's going to equal 1/2 times the mass times the radius. The auxiliary disk will use the same equation, and the ring will be equal to just mr squared, so it's the mass times the radius squared. We have our values. Now we're going to measure the accelerations experimentally that these disks have. I'm going to do a few trials of each to show how we would do this, and then I will provide you with more data afterwards, so you don't have to watch how to do each one of these. So we're going to start off over at the linear speed. I'm going to attach a 100-gram mass to this, and I'm going to make sure that I'm on the largest step pulley. We are going to place that over top of the pulley and make sure that it isn't there, the screw down lower is not interfering, nor is the cord that is connecting. You can see it starts to spin very freely here, very, very low friction. So we get everything out of the way, and again, I'm going to double check that I'm on the largest pulley, which I am. And so I'm going to hit record. I want to stop recording before I stop the wheel. So I'm going to start the wheel, start the record, stop the record, stop the wheel. So here we go. Wheel started, record started, go. So we'll do it again. Start, start, stop, stop. So we get some nice data. The one reason we do that is for timing. We get a much cleaner run. This one did dip at the end. I think I stopped slightly fast. So we can start it, stop, stop. So with this, we can now take and measure. And so I get an acceleration here of about 0.15. So we'll record that value. We'll do it again. Stop, 0.112. We'll do it again. And again, I stopped that one a little early, so you saw the drop off, so I'm going to have to highlight. One of the advantages there was not to do that. 0.121. Okay, and we just keep making these measurements. We do the same thing with the ring on here. We are going to wind this up, and we're going to release it with the ring. So I hit record, start it, stop, 0.0903. And that actually goes on the ring measurement, so that would go over here, 0.0903. And then for the main disk, we just place the main disk on top. Again, I'm going to give you a full set of data so you don't have to watch every one of these measurements be taken. So here we go. 0.0637. And we get our measurements as we go along here. From there, once you've done all of these trials, you are then going to do the calculations, which
We're now going to go through the calculations in the spreadsheet program. Before we go into new calculations, I did make a minor mistake in the previous portion of this video. For the main disk, I should have done 1/2 mr squared. I only did 1/2 mr. So note that I've adjusted the calculation to include both C8 times C8, or I could have done times C8 caret 2. So 1/2 mr squared for the main disk, 1/2 mr squared for the auxiliary disk, and mr squared for the ring. So make sure you make those modifications. So now I've calculated the inertias. Now I'm going to use the measured acceleration data to look at the experimental moment of inertia. So to do this, I'm going to average out the measurements. So I type in equals average, open parentheses, and I highlight all of the data, hit enter. I then pull this sideways so that I have it auto calculated for the main disk and the auxiliary and the main disk and the ring. I now come down to the calculated moments of inertia. And so I'm going to hit equals, and I'm going to come up to the top, and I'm going to hit calculated moment of inertia for the main disk. And then this would auto-fill down, but there's one modification that needs to be made here because this is the main disk and the auxiliary disk. The value we're seeing over here is only the main disk, so I need to add in the main disk to that auxiliary disk. So I have done that now, and I'll do the same for the main and the ring. So it's going to be the value I currently see on the screen, the D10 value, plus the main disk. So at this point, I've concluded both the main disk and the auxiliary disk in this calculation, the main disk and the ring. The accelerations are going to come from the averages. I can't autofill this down since they're horizontal. So I have to click on each one, but I'm going to use the program. So if there was ever a case where I have to make a modification, it would auto change down below. So if this was, for example, 20, it auto changes down here without me having to go back and do that manually. The tension is going to equal mg minus ma. Looking at the equation sheet, this is where we do the mass that was falling. We used 100-gram mass, so that's 0.1 kilograms times 9.8 minus 0 times 0.1 times the acceleration, and we get a value here, and the 0.1 times 9.8 times the acceleration, which I clicked on, it didn't grab it. There we go. That's the correct value. 0.1 times 9.8 minus 0.1 times the acceleration. The torque is going to be equal to the tension that we see divided by the radius of the step pulley times the radius of the step pulley. Force times the radius. And so when we do that, we need to know the radius of the step pulley. I did measure this. The step pulley we were using was 2.5 centimeters in radius, 2.5 centimeters in radius. So it would be the tension times 0.025, and that gives us our value of torque. So at the point where the string is attached to the step pulley under the main disc, it has a radius of, again, 2.5 centimeters. The angular acceleration is going to equal the linear acceleration divided by that radius as well. And so that radius is, for the step pulley, is 0.25. And so that works out. So now we have the angular acceleration of the step pulley system. And then from there, we know the torque and the angular acceleration, so we can find the moment of inertia. The moment of inertia is equal to the torque divided by the acceleration. In our equation, angular acceleration is equal to the torque over the moment of inertia. We manipulate that Newton's second law for rotational motion. And so the torque divided by the angular acceleration does give us the moment of inertia. And we will fill that down, and we now have our values. And so what we're going to do is we're going to compare these values using percent error. So the value down here will be the same as the values above for the calculated. I don't need to make the adjustment for the main disk and auxiliary disk. Again, it's already been done. I then can find the experimental value, or put the experimental value in this location, same way. So I grab hold of it and I pull down, and then I do percent error. And so for percent error, I'm going to do the absolute value of the calculated minus the calculated, which is the theoretical value, two parentheses because the numerator, calculated minus the experimental. When I close that parentheses, that's my numerator, divided by the denominator, which is the calculated. Close that up, multiply by 100, and I get my error, which is about 8.73%, 2.7%, and 4.6%. These are reasonable. We were dealing with very small masses that were pulling the 100 grams, and with our system, we obviously have some error built in with some friction. So these are reasonable percent errors for this. So you're going to use your own set of data on this, which you will either measure yourself or I'll provide for you, and then we will take that information and submit it in a traditional lab format. If you have any questions, please let me know. Have a wonderful day.